January 5, 1933. The winds swept across the Golden Gate Strait like invisible hammers, ripping through the survey crews who struggled to anchor their instruments on the jagged cliffs of Marin County. The air was thick with fog, so dense it swallowed the horizon and blurred the line between sea and sky. Below, the bay churned with relentless currents strong enough to overturn small boats, while tides could rise more than 20 feet in hours, transforming calm waters into surging walls of force. For decades, engineers had tried and failed to find a solution for this treacherous passage, each set of calculations arriving at the same grim conclusion. Spanning the Golden Gate with a bridge was impossible. Yet Joseph Strauss, a 50-year-old engineer with a reputation for audacity and unshakable confidence, arrived with blueprints that defied conventional wisdom. His design envisioned a suspension bridge nearly 2 miles long, with towers rising 746 feet above the water, higher than any structure on the West Coast at that time. The scale alone was unprecedented, but Strauss's plan went further. It accounted for the ferocious winds, seismic activity, and salt-laden fog that would batter the bridge daily. He proposed massive suspension cables that could flex and absorb energy, towers anchored into bedrock hundreds of feet below the water, and roadway trusses designed to handle the dynamic forces of traffic, wind, and earthquakes. Skeptics were relentless. European engineers, many with decades of experience in steel and suspension bridges, scoffed at Strauss's audacity. American peers were equally doubtful. "The winds alone will tear the bridge apart," they warned. "The currents will destroy the piers before they are even completed. No steel can survive this salt air for more than a decade." Newspapers labeled the project Strauss's folly, a gamble that threatened both human lives and public funds. But the stakes went beyond professional pride or technical ambition. San Francisco, still reeling from the devastation of the 1906 earthquake, and now gripped by the economic despair of the Great Depression, needed a bridge not merely as an architectural statement, but as a lifeline for commerce, connection, and survival. Strauss knew that the Golden Gate Bridge would not allow shortcuts. Every decision mattered. The placement of towers had to account for underwater currents and earthquake risk. The thickness and tension of each cable would determine whether the deck could sway without snapping. Even the diameter of rivets was critical to the bridge's structural integrity. One miscalculation, one underestimated gust, or one flawed connection could doom the entire project. Yet Strauss's mind worked differently from others. Where skeptics saw insurmountable obstacles, he saw challenges to be quantified, tested, and mastered. As he stood surveying the bay, Strauss imagined the bridge rising above the fog like a silver thread, linking San Francisco to the North Bay and beyond. He envisioned cranes hoisting steel beams hundreds of feet above the water, workers threading cables in relentless winds, and towers anchored into solid rock beneath waves that had defeated every previous attempt. The path ahead demanded courage, precision, and a vision few could comprehend. This was not just a bridge, it was a testament to human ingenuity, a challenge against nature itself, and a gamble that would either cement Strauss's legacy or become a cautionary tale whispered among engineers for generations. Even before a single rivet was driven, the Golden Gate Strait had already earned its reputation as an unyielding adversary. Yet for Strauss, impossibility was merely the starting line. The real battle lay ahead, against currents, winds, earthquakes, and time itself, and he was ready to meet it with every ounce of skill, daring, and determination at his command. Building the Golden Gate Bridge was not simply a feat of design, it was a confrontation with nature itself. From the very beginning, the waters of the Golden Gate Strait seemed determined to resist human ambition. Strauss and his team faced an environment where ocean currents churned with ferocious speed, tides shifted unpredictably, and the water depth reached levels few engineers had ever attempted to anchor a bridge into. To secure the towers, Strauss insisted on foundations sunk deep into the rocky bed, more than 100 feet below the surface, requiring workers to descend into pressurized caissons, steel chambers filled with compressed air that held back the river yet pressed down with a suffocating force on every inch of the body. Inside these chambers, the air was dense, the work grueling, and decompression sickness, a cruel malady later called the bends, haunted every shift. Workers risked paralysis or death with every hour spent beneath the water, a peril few contemporary projects demanded and one that cast a shadow of mortal danger over the entire construction site. Above the water, another battle raged. Steelworkers, riveters, and engineers operated hundreds of feet above the bay, often in freezing fog that rendered towers invisible until they were nearly upon them. Each rivet driven, each steel beam hoisted into place carried not only the physical weight of the bridge, but the collective skepticism of the world's engineers. Critics doubted whether a suspension spanning over 4,000 feet could endure the relentless wind, earthquakes, and ocean spray that characterized the site. Yet the crew pressed on, performing feats of precision and courage that would define the bridge for generations. Perhaps the most ambitious and perilous operation was the spinning of the main suspension cables. On site, the team twisted together over 27,000 individual wires to create each single, unyielding line capable of supporting the entire roadway. Workers guided these wires across towers hundreds of feet tall, while gale-force winds lashed at their bodies, trying to tear the cables from their grips. Dense fog could appear without warning, obscuring the towers entirely and leaving men suspended in near total invisibility over the churning bay below. The ocean's currents threatened the very scaffolding and anchor points that held the cables in place, demanding constant vigilance and ingenuity. Strauss's approach combined audacious engineering with innovative safety measures that were revolutionary for the time. He introduced the use of a safety net beneath the bridge deck, a single decision that would save 19 lives, a record unprecedented on projects of such scale. Anchoring techniques were refined to distribute immense weight evenly across the towers, preventing localized stress that could have led to collapse. Rivet heating methods were timed with near mathematical precision, ensuring that each connection fused perfectly to maintain the bridge's structural integrity under extraordinary loads. Every bolt, beam, and cable became part of a carefully orchestrated experiment, testing not just the strength of steel, but the courage, skill, and endurance of every man involved. The Golden Gate Bridge's construction was as much a story of human endurance as it was of engineering genius. Every day, workers faced danger in multiple forms: falling steel, snapping cables, pressurized caissons, icy winds, and treacherous currents, all while performing tasks that required precision on a scale that had never been attempted before. The psychological strain was immense. Men had to trust both the calculations of engineers they barely knew and the rivets they drove with their own hands, knowing that the smallest mistake could be catastrophic. Yet, despite these perils, the work continued, driven by a combination of personal bravery, professional pride, and the belief that they were creating something that would endure long after they were gone. In the end, the engineering battles of the Golden Gate Bridge were not just against gravity, wind, or water. They were battles of vision against doubt, courage against fear, and human skill against the raw forces of nature. The bridge rose, inch by inch, wire by wire, to become a monument to the extraordinary effort, planning, and determination that made its longevity possible. Without the human element, each riveter, engineer, and visionary leader, there would have been no bridge to survive storms, earthquakes, and decades of relentless environmental assault. The Golden Gate Bridge's longevity was no accident. Every element of its design reflected a deep understanding of the challenges posed by one of the world's most unforgiving waterways. Strauss and his engineers did not simply aim to span the Golden Gate Strait. They sought to build a bridge that could endure decades of relentless environmental stress, constant traffic, and the unpredictable forces of nature. The suspension system itself was revolutionary. Unlike rigid structures that resist wind, the Golden Gate was engineered to flex, to bend and sway in response to gusts rather than fight them. The main cables, stretching nearly 7,000 feet from anchor to anchor, were designed to absorb and dissipate energy, allowing the bridge deck to vibrate subtly without transmitting destructive forces to the towers. This flexibility turned what could have been a fatal weakness into a defining strength, ensuring that hurricane-force winds, which often swept across the strait, would leave the bridge standing rather than shaking it apart. Beneath the roadway, reinforced trusses added an extra layer of stability. These steel frameworks were designed to resist twisting and lateral movement while maintaining the bridge's elegant, airy profile. By distributing weight efficiently and allowing for controlled motion, the trusses worked in harmony with the suspension system to protect the structure from the constant dynamic forces imposed by trains, automobiles, and even seismic activity. Each design decision reflected foresight. Engineers were not simply building for the present, but for decades and generations into the future. Materials were selected with extraordinary care. The steel itself was formulated to resist the corrosive effects of salt-laden air and heavy fog that blanket the bay for much of the year. Long before modern anti-corrosion coatings existed, Strauss's team applied a thin but durable layer of protective paint designed to slow oxidation and prevent rust from taking hold in critical joints. Rivets, beams, and cables were manufactured to exacting tolerances, with meticulous inspections to ensure that every piece met the rigorous standards necessary for permanent construction. The engineers also understood a subtle but critical truth. Bridges often fail not from dramatic catastrophes, but from cumulative, almost invisible, stresses. A small crack forming in a steel beam, a joint slowly succumbing to moisture, or minute misalignments accumulating over time, these were the hidden killers of modern infrastructure. To counter them, the Golden Gate's construction demanded quality control at every level, from laboratory testing of raw materials to precise installation methods on the cliffs and towers hundreds of feet above the water. Each cable strand, each rivet, each steel beam was part of a system designed to endure decades of cumulative wear. In many ways, the bridge's design philosophy contrasted sharply with modern practices. Today, many bridges are optimized for speed, cost efficiency, or minimal maintenance within a limited lifespan. Preventive measures are often sacrificed to save months of construction or millions of dollars, leaving vulnerabilities that compound over time. The Golden Gate Bridge, in contrast, was built with patience, foresight, and a commitment to excellence that modern efficiency-driven projects rarely replicate. It was this combination of engineering insight, material foresight, and human precision that allowed the Golden Gate Bridge to survive where others might have failed. The flexible suspension system, reinforced trusses, corrosion-resistant steel, and rigorous quality control were not just innovations. They were a statement, a bridge designed to endure not decades but a century and more. And over the years, as storms, wind, and traffic put the bridge to the test, it proved that careful, deliberate design could triumph over forces that modern shortcuts and cost-cutting measures cannot overcome. When the Golden Gate Bridge officially opened in May 1937, it was immediately clear that it would not be spared the harsh realities of its environment. The strait it spanned is a corridor of extremes, where ocean currents collide with tidal surges and fog rolls in almost daily, thick enough to obscure towers from view. Seasonal storms brought hurricane-force winds that swept across the bridge deck, sometimes exceeding 70 miles per hour, while waves rising over 20 feet crashed against the piers with relentless energy. Lesser bridges would have faltered under even a fraction of this onslaught. From the very beginning, the bridge was tested not just by weather, but by the constant demands of human activity. Cars, trucks, and trains, though lighter in the 1930s, crossed in growing numbers, adding dynamic stress to the structure. The combination of moving loads, shifting winds, and seismic tremors could have spelled disaster if Strauss and his engineers had relied on rigid conventional designs. But the Golden Gate Bridge was different. Its flexible suspension system absorbed gusts that might have torn through a more brittle construction, distributing energy through its cables rather than forcing it into the towers. The towers themselves, though massive, were designed to sway imperceptibly, bending in harmony with the forces around them rather than resisting stubbornly. Even the deck, which carried traffic day and night, remained remarkably level. its reinforced trusses quietly dissipating vibrations and torsion that could have fractured lesser steel frameworks. Earthquakes presented another formidable threat. The San Francisco Bay Area is one of the most seismically active regions in the United States, and the Golden Gate Bridge sits squarely on fault lines capable of shaking structures violently. The bridge's design, refined through years of calculations and iterative engineering, accounted for these forces long before advanced computer modeling existed. The suspension cables acted like giant shock absorbers. The tower's foundations allowed slight movement, and the deck flexed just enough to prevent concentrated stress. When quakes struck, the bridge remained steadfast, confirming the accuracy and foresight of Strauss's vision. Storms in the decades following its opening provided repeated real-world tests. In the 1950s, howling winds and pounding surf battered the piers and deck, yet the bridge weathered the storms with only routine inspections and maintenance. The 1980s brought similarly violent conditions, including wind gusts that would have toppled older suspension bridges, yet the Golden Gate remained unshaken. Its secret lay not only in design, but in materials. The steel used for the bridge contained early corrosion-resistant treatments, and a protective paint layer, applied meticulously and reapplied by generations of maintenance crews, slowed the advance of rust long before modern coatings made corrosion control a standard practice in civil engineering. These measures, though simple in principle, created durability few modern bridges achieve. The Golden Gate Bridge also thrived in conditions that modern engineers would consider punishing. The combination of salty ocean air, fog, and constant vibration could have quickly degraded conventional steel. Modern bridges, designed for cost efficiency or shorter lifespans, often experience structural issues within 2 or 3 decades, including cracking, fatigue, and corrosion, necessitating expensive repairs. By contrast, the Golden Gate exemplified a design philosophy centered on longevity rather than minimum compliance. Every decision, from the composition of the steel to the flexible geometry of the towers, was calibrated to withstand not just the ordinary, but the extraordinary stresses of nature. In this way, the bridge became a testament to the principle that engineering for permanence requires anticipation, foresight, and an uncompromising commitment to quality. Every gust of wind, every earthquake tremor, and every roaring tide that struck the Golden Gate over decades became a proof point, demonstrating that meticulous design, material integrity, and a deep understanding of environmental forces could produce a structure capable of outlasting modern bridges built with newer technology but far less resilience. The Golden Gate did not merely survive nature's tests, it thrived under them, proving that human ingenuity, when combined with careful planning and precise execution, can create infrastructure that endures far beyond the expectations of its time. The story of the Golden Gate Bridge is also a story of human skill and courage. Thousands of workers risked life and limb every day, often hundreds of feet above frigid, churning water. Steelworkers maneuvered beams weighing tons with the precision of clockmakers. Rivets were heated to glowing red and hammered into place with near-perfect synchronization, and cable-spinning crews adjusted for wind, temperature, and tension with painstaking care. Strauss himself spent countless hours on site, ensuring that every calculation translated into reality. Modern bridges rely heavily on machinery, software, and prefabrication, but they often lack the direct human oversight and dedication that allowed the Golden Gate to endure. Each hand-driven rivet, every wire in the main cable, and every bolt in the deck became part of a living system, combining ingenuity, skill, and instinct in ways machines alone could not replicate. This human element was just as crucial as the steel or the design. Without the workers' courage, the bridge might have existed only as a blueprint, never a reality. Nearly a century later, the Golden Gate Bridge stands as a benchmark in structural longevity. Modern bridges, despite digital modeling, advanced materials, and rapid construction techniques, often show cracks, rust, and fatigue within decades. Some require major repairs within 15 to 30 years, while the Golden Gate continues to endure heavy traffic, storms, and seismic events with routine maintenance alone. Engineers still study its suspension system, tower design, and foundation techniques, searching for lessons lost in contemporary efficiency-driven projects. The difference lies not in the absence of technology, but in the philosophy. 1930s engineers built for permanence, prioritizing careful material selection, labor oversight, and rigorous testing. Today's bridges are often optimized for speed and cost reduction, trading durability for short-term gains. The Golden Gate is proof that a structure built with meticulous care, attention to detail, and human oversight can outperform modern methods by decades, sometimes nearly a century. Standing today, the Golden Gate Bridge is more than a roadway. It is a living testament to engineering mastery, human skill, and foresight. Its steel towers, cables, and deck have endured countless storms, earthquakes, and tidal forces that might have crippled other structures. Every inch of riveted steel reflects meticulous craftsmanship and careful calculations, reminding engineers that speed and cost-cutting cannot replace careful planning. Strauss's vision, executed through courage and ingenuity, continues to inspire. Modern infrastructure projects frequently struggle to achieve even half the lifespan of this bridge, despite advanced materials and computer simulations. The Golden Gate remains a monument to what happens when engineering meets human determination, when every calculation, rivet, and cable is executed with an eye toward permanence. Nearly a century after its opening, it still carries traffic safely, still draws admiration from engineers around the world, and still teaches the enduring lesson. When human skill, meticulous design, and durable materials combine, structures can truly stand the test of time.